Okay, let's just dive right into this. I want you to do me a favor. Close your eyes for a second. Imagine you're floating in the absolute deepest, emptiest corner of intergalactic space. It is pitch black. I mean, no stars nearby, no planets, literally zero landmarks whatsoever. Just you drifting in an endless, ink-black void. Welcome to This Explainer. Today, we're going to tear down the cosmic illusion of speed and, honestly, fundamentally rethink the very ground beneath our feet.
So you're floating out there in this absolute nothingness, right? Let me ask you a direct question. How fast are you moving right now? Think about it. There's no wind rushing past your face because, there's no air. There's no ground to measure your steps against. You feel completely weightless and perfectly still. But then, out of nowhere, a stray metallic space wrench drifts past your face. Relative to you, it looks like it's moving at a leisurely walking pace, maybe 5 kilometers an hour. But wait a minute. Is the wrench moving or are you moving? If we could ask the wrench, it'd probably swear it is perfectly still and you're the one flying by. Without an anchor, the whole concept of speed just completely unravels.
To really wrap our heads around this void, let's come back down to Earth for a second. Because reality completely shatters our everyday illusion of sitting still. Like, if you're on your couch right now watching this, you feel stationary, yeah? Well, the Earth is spinning, so you're actually moving at 1,670 kilometers per hour. Oh, but we are also orbiting the Sun at an absolutely astonishing 107,000 kilometers per hour. And it doesn't even stop there. Our entire Milky Way galaxy is actively being pulled toward a massive gravitational anomaly called the Great Attractor at roughly 2.1 million kilometers per hour. So, are you sitting still, or are you traveling at over 2 million kilometers an hour? The wild, counterintuitive answer is you're doing both. Speed depends entirely on what you decide to measure your movement against.
And this actually brings us to a really brilliant realization from way before Albert Einstein. Back in the 1600s, Galileo proposed this fascinating thought experiment. He basically said, imagine you're locked inside the main cabin, below decks on a massive windowless sailing ship. And this ship is gliding on a perfectly smooth, glassy sea. No waves, no turning, just smooth, constant motion. If you drop a coin in that cabin, it falls straight down. If you play catch with a friend, it feels exactly the same as if the ship was parked right at the dock.
What Galileo is illustrating here is what we call an inertial reference frame. Basically, that's just a formal way of saying a state of motion that isn't accelerating. He realized that the laws of physics are exactly the same in all inertial reference frames. So to you, inside that windowless ship, you are perfectly at rest. But to a spectator standing on the shoreline, you, the coin, the ball, you're all speeding by. The crucial takeaway here is that speed isn't some intrinsic property written into an object's DNA. It's just a relationship between two different frames of reference.
Now, historically, this incredibly elegant idea ended up building into one of the greatest crises in the history of science. Because for centuries, Galileo's relativity worked perfectly, right? If you're on a train going 80 kilometers an hour and you throw a ball forward at 20, someone outside sees that ball moving at 100. You literally just add the speeds together. Super simple. But in the mid-1800s, scientists figured out that light acts as a wave, and every other wave we knew about needed a physical medium to travel through. Sound has air, ocean waves have water, so they just assumed space had to be filled with this invisible stationary medium. They called it the luminiferous ether, and they figured, hey, if this ether is the stationary background of the universe, we can finally measure our actual speed against it.
So, to prove this was real, in 1887, Albert Michelson and Edward Morley set up this brilliant experiment. The logic was, if the Earth is moving through this stationary ether, there has to be an ether wind, and that wind should slow down light, kind of like how swimming against a river current slows you down. But the actual result? Absolutely nothing. Zilch. The speed of light was exactly the same in every single direction. The Earth's motion didn't affect it whatsoever. Physicists were completely baffled.
Enter young Albert Einstein in 1905, dropping a completely radical revelation on the scientific community. Instead of trying to force this ether idea to make sense, Einstein just said, look, the ether doesn't exist. Instead, the speed of light is a strict, fundamental constant, roughly 300,000 kilometers per second, period. No matter how fast you are flying in a spaceship, if you shine a flashlight forward, that beam of light leaves you at exactly 300,000 kilometers per second. And the crazy part? Someone standing perfectly still outside, watching you fly by, will measure that exact same beam of light moving at that exact same speed.
Now, if you're sitting there thinking, wait, how is that logically possible? You are definitely not alone. Just think about the basic math. Speed equals distance divided by time. If speed is completely locked and permanently fixed for light, then the other two variables in that equation, distance and time, they can't be fixed. They literally have to be flexible. They have to bend.
Let's actually walk through the famous light clock thought experiment to visualize this. Imagine a clock inside a spaceship, but instead of a pendulum, a single photon of light is bouncing straight up and down between two mirrors. To you, inside the stationary ship, the light just moves in a simple, straight vertical line. But what if that spaceship is zooming past an observer out on a space station? From their perspective, that photon isn't just going straight up and down anymore. It has to trace this longer, zigzagging diagonal path just to keep up with the moving mirrors. And here is the real mind-bender. Because the speed of light must remain perfectly constant, but the light is traveling a longer distance, it must take more time. From the outside observer's perspective, time literally slows down inside your spaceship.
Which brings us to the formal definitions that quite literally change the world. This is time dilation, the phenomenon where time actually passes slower for an observer in a moving reference frame compared to a stationary one. And it's not just time, by the way. Space itself compresses along the direction of motion, which is known as length contraction. Distance and time literally bend and warp to guarantee that the speed of light stays perfectly constant for everyone, everywhere. Einstein's ultimate paradigm shift here was realizing that space and time are not some rigid, unchanging stage that we just exist on. No, they are woven together into this fluid, dynamic, four-dimensional fabric called space-time. Your personal experience of here and now is heavily influenced by your specific state of motion. And because of this, a universal master clock or a master ruler, it simply doesn't exist. The whole concept of an actual speed is a physical impossibility.
But wait a minute, human curiosity is pretty stubborn, right? We want a cosmic loophole. We think, well, what if we look at the absolute oldest thing in existence? Enter the cosmic microwave background, or the CMB. This is the leftover thermal radiation from the Big Bang. It's essentially a baby picture of the universe from when it was just 380,000 years old. It's this faint, uniform glow that fills literally every single cubic centimeter of space. So, could this be our ultimate stationary anchor?
We can actually try to use the CMB as a sort of cosmic speedometer by looking at the Doppler effect. Think about how an ambulance siren sounds higher-pitched as it speeds towards you and lower as it drives away. Light waves do the exact same thing. Moving toward a light source compresses the waves, which shifts them toward the blue end of the spectrum. We call that blue shift. Moving away stretches those waves out into red shift.
And when astrophysicists map the CMB, they actually see this. One side of our sky is slightly blue-shifted, and the opposite side is red-shifted. It's called the CMB dipole anisotropy. By measuring this shift, we can calculate our solar system's precise movement relative to this ancient sea of background radiation. The number? Roughly 370 kilometers per second. So, have we finally done it? Have we found our true, actual speed through the universe? Nope. Sorry to smash that false hope right here. As incredibly convenient as the CMB is for cosmologists trying to map the universe, it is absolutely not an absolute frame of reference. The fundamental laws of physics do not care about the CMB. If you run a physics experiment in a lab flying at 99% the speed of light relative to the CMB, physics works exactly the same. The CMB is just a giant cloud of ancient energy. Measuring your speed against it is really no different than measuring your speed against a passing train or the air inside a room. The universe still aggressively refuses to give us a fundamental zero point of motion.
And if your mind isn't stretched quite enough yet, let's hit our final twist. This one comes courtesy of Edwin Hubble in 1929. Turns out, space itself isn't even static. The universe is expanding. But here's the kicker. Distant galaxies aren't actually flying away from us through space. The fabric of space itself is stretching between us. Think of it exactly like raisins in rising bread dough. The raisins aren't swimming through the dough. They're stationary relative to the dough right around them. But as that dough expands in the oven, every single raisin just gets further away from every other raisin.
In cosmology, this rate of stretching is defined as expansion velocity. And because this stretching is happening everywhere all at once, there is so much space expanding between us in extremely distant galaxies that they actually appear to be receding from us at speeds exceeding the speed of light.
Now you might be thinking, hold on a second, I thought the speed of light was the ultimate cosmic speed limit. Well, it is. But Einstein's limit only applies to objects traveling through space. Space itself, the fabric of the universe, it can stretch and warp at absolutely any speed it wants.
If you were sitting in one of those distant galaxies looking back at us, you would feel completely stationary, and you would see our Milky Way receding faster than light. When the very yardstick you are using to measure distance, space itself, is literally stretching, the question of who is actually moving completely loses its meaning.
So, we arrive right back where we started, floating out in that dark void. Asking for your actual speed is like asking if a cup of coffee is to your left or your right without knowing which way you're facing. Left, right, fast, slow, they aren't properties of objects, they are just relationships. And honestly, I think there's a profound beauty to a universe without an absolute center and without an absolute rest frame. It means no perspective is privileged over another. Whether you're down here on Earth or drifting in the void between galaxies, your viewpoint is perfectly valid. Which leaves me with a final thought to spark your curiosity today. If every perspective in the cosmos is equally valid and purely relative, what frame of reference are you measuring your life against today?
Please like and subscribe.